Welcome to our first activity on the category of vector spaces, where we are going to study basic techniques to prove or disprove that a function is linear. Our first example is a simple function from r squared to r squared. Let phi be the function which, to a vector of coordinate xy, assign the vector of coordinate 3x plus y, x minus y. We wish to prove that phi is linear. From our first lecture, we learned that phi is linear if and only if, for any pair of vectors v and w from r squared, and for any scalar lambda, phi of lambda v plus w is equal to lambda phi of v plus phi of w. So, we take two arbitrary vectors in r squared, denoted by xy, y1, and x2, y2, and an arbitrary scalar lambda. We then follow the characterization of linearity. We compute phi of lambda times our first vector plus our second vector. We simplify the argument of phi using the vector operations on r squared. We then actually apply phi. And we then try to make the quantity of phi of x1, y1 and phi of x2, y2 appear, and guided by the characterization of linearity, the trick is to try and factor lambda. This is the expression that you naturally obtain. You cannot factor lambda from every term, but that's to be expected, and we recognize from this expression that you get lambda phi of xy, y1 plus phi of x2, y2. Since this is true for any arbitrary pair of vectors in R squared and any scalar, we have indeed shown that phi is linear as desired. Sometimes you will want to show that a map is not linear. We have a characterization of linearity, so if we take its negation, we get a characterization of nonlinearity. A map phi is nonlinear if you can find a pair of vector v and w and a scalar lambda, such that phi of lambda v plus w does not equal lambda phi of v plus phi of w. So this gives us a general technique to disprove that a map is linear. In practice, you disprove a map is linear by showing that it does not possess one of the many properties of linear maps. For instance, every linear map must map 0 to 0. Therefore, if a map phi does not map 0 to 0, phi is not linear. Another property, of course, is that maybe phi does not respect the scalar multiplication, meaning you can find a vector v and a scalar lambda such that phi of lambda v does not equal lambda phi of v. Or maybe phi is not additive, meaning that you can find a pair of vectors such that phi of their sum is not the sum of their images by phi. There are many other properties we are going to learn about linear maps, and as we learn more about linear maps, other properties may fail and may be used to disprove a particular map is linear or not linear. So, as an exercise, let's look at this little example. We ask if phi is linear. What we can observe on this little map is that if we apply it to two vectors, the vector 1, 0, 0, and the vector 2, 0, 0, well, we can easily calculate the output. But while the input vectors are related to each other by a factor of 2, that is 2 times 1, 0, 0 is equal to 2, 0, 0, the outputs of applying phi to these two vectors are not related in the same way. Phi of 1, 0, 0 is 1, 1, 1, twice that would be 2, 2, 2, yet phi of 2, 0, 0 is in fact 2, 2, 4. So there is at least a vector and a scalar, namely here the vector 1, 0, 0 and the scalar 2, so that phi of twice the vector is not equal to twice phi of that vector. That means that phi cannot be linear. Another example is this other little function, and you immediately notice that the second coordinate of the image here has a x plus 1 expression, so it's easy to see that probably this is not going to be linear, and indeed, all you have to do is calculate phi at 0. You immediately get that phi of 0, 0, 0 is the vector 0, 1. That's not the vector 0, so phi is not linear. This concludes this activity.